Hello, we're going to get started on the last section in Focus 7. So this is on the third kind of motion. So we looked at how translational motion, something moving through space, is quantized if there are restrictions on where the particle can go. Rotational motion is quantized, and now we'll talk about vibration. So that motion that we can use to model the vibrational energy in a molecule. Okay, so this is topic 7E, vibrational motion. And the important thing that will come out of this, we'll see the same concepts. We'll see the energies quantized because of boundary conditions. And we're going to use the harmonic oscillator as our model, and we'll look at that in a second. But the important parts are so the key idea is that the energy of the harmonic oscillator is quantized, and we're going to see something different. The particle in a box and rotational motion in 2 and 3 dimensions didn't have any tunneling going on, but we're going to see here that an oscillator can be extended or compressed into regions that wouldn't be allowed classically. So we're going to see tunneling essentially within a system. So let's start here. So the model is going to look like this right here. At the bottom, we have this potential energy surface written in red, which means there's an equilibrium distance at which a spring or an atom vibrating against another atom would mostly exist at. But you can extend it beyond, so you can make it longer, or x getting smaller in this direction, you can compress it. And so we can use this function for this red surface as our potential energy when we solve Schrodinger's equation. I think it's easiest to see it where I wrote it out a little bit bigger. So the function for that red curve, is actually 1/2 some force constant times x squared. So the potential energy depends on where you are. It can either be stretched or compressed, but when you get to these boundaries, there isn't enough energy for it to stretch any further. And when it's compressed, there isn't enough energy to compress it any further. So if you think about it, the stretching is destroying those interactions of the electrons that we think of as forming bonds. And when it's compressed, you're essentially starting to make it so that the nuclei see each other. And that's a very strong repulsion. So it's not going to have enough energy to compress too far. So when we solve the quantum mechanical system, we are solving this Schrodinger equation. So we have the kinetic energy, so the movement of the two particles or the spring stretching, plus this is the potential energy for harmonic oscillator as a function of x. You multiply that by psi, and those two terms on the left-hand side, those operations have to give you back a constant times the function. This one's not so easy to solve or even see how the boundary conditions impact it, but a mathematician solved it way back when most of quantum mechanics was solved by physicists and mathematicians rather than chemists. So turns out that the energy is quantized, and this is V. It's very hard to see the difference in your book, and this is nu. So this is the frequency of the vibration, this is Planck's constant, and this is a quantum number V. So V can go from 0, 1 by integers. So when they solve this problem, just like the other two we solved, you'll see restrictions. So there are only some possibilities for energy. The frequency of a vibration is related to the force constant. So essentially how stiff this spring is, and then the mass of the particle that's vibrating. So I guess we'll look at this self-test. Self-test just asks you to determine a force constant. So this is self-test on page, on page 348. And it says the vibrational frequency of an HI bond is 69.55 terahertz. Estimate the force constant for the bond on the basis that only the hydrogen atom moves. So we're essentially assuming that, which is pretty common, that if you have iodine and hydrogen, that the iodine is so heavy that the hydrogen is essentially just vibrating against the iodine as if it was a brick wall. It's stationary. So when we use this equation, we have the frequency, we want the force constant. So we put the frequency in hertz, which is, as you may remember, equal to 1/seconds. And I'm just gonna make sure that I use all SI units. And then I'll know that my force constant comes out in newtons per meter because that's the SI unit of force. So just plug in the values. So we have the frequency, 1/2 pi, the mass of one hydrogen atom, not a mole, and then we have to take the square root. And I got 318 newtons per meter. So the energies are quantized, and the wave functions are given in this table on page 349. Let's see if we can zero in on them. They're all Gaussians, and everything except the ground state has a polynomial in front of it. It's called the Hermite polynomial. Yeah, you can see that. So each of them has this Gaussian part. And then they get more and more complex as you get to bigger quantum numbers. And so over here, they've graphed these. So the ground state is just a Gaussian. The first excited state has one node. Second excited state, 2, 3 as you go up. So when you look at the probability, what you see from these wave functions is when you're in the ground state, you have the greatest probability of seeing the particles at their equilibrium distance. As you go up one, if you square this function, you have equal probabilities on both sides of the middle, but 0 in the middle, so that's strange. Probably the strangest thing about it is as you think about this, if the particles are stretching and compressing beyond where they'd be at equilibrium, then as they stretch, they slow down, and then they stop and they turn around. And the same thing, they compress, they slow down, they stop, and they turn around as the kinetic energy becomes potential energy. So that's exactly the opposite of what this shows in the ground state. You would think if it's slowing down as it turns around, both at extension and compression, that it would spend more of its time stretched and compressed to those lengths, and that you'd have a greater probability of finding it closer to the potential energy walls. So this is showing something very non-classical, that you find it more likely to be in that place in the middle where it's actually going the fastest, so it should spend the least time there. The Bohr correspondence principle, just like we looked at for the particle in a box, shows as you get higher and higher and higher and you get larger V's, the wave function starts to look like this. And yes, indeed, you get bigger peaks on the side and a more uniform distribution. And so this is showing what we've mentioned before, that as you go to excited states, things start to look more classically. So just like we'd predict, it should spend more time at the turning points and have a more uniform distribution than the ground states show. So let's just talk about these solutions a little bit. So it does not want to focus. Maybe I won't. Maybe I'll just assume I can read it to you. I know right now it's not really responding. Huh. I am sorry, something seems to be kind of wackoed with the camera. Let's take it back up there, see. Well, that's not so great. So on page 349, I'm not sure why it's not focusing. Okay, I'm just gonna read the left-hand column, which talks about these wave functions and their properties. So the first concept is that the lowest energy wave function is just a Gaussian. The particle is most likely to be found in the middle at x equals 0, but may be found at greater displacements with decreasing probability. The first excited state has a node at x equals 0. So at x equals 0, the first excited state has a 0 at x equals 0. You have 0 probability of finding it there. All the wave functions extend beyond, and I am going to have to focus this for that. I guess you can see it. So you look in the upper right-hand corner on page 349, each of these wave functions has value other than 0 outside the blue potential energy line. So that means they have negative kinetic energy, basically, in order to have enough energy to overcome the fact that they should have turned around and started to compress when they hit the blue line's separation distance. So when you look at each of these, you'll see a probability of finding the particles stretched or compressed beyond what classical limits would tell you would be possible. And that is all that we're going to talk about for vibrational energy. So we're going to go on next to focus 8, and we're going to talk about the hydrogen atom, and we're going to look at the solutions to that. They'll have some similarity to what we've done here. We'll use the rotational solutions for part of it. And then as we go deeper into quantum mechanics in this class, we'll see that the harmonic oscillator can be used to explain IR spectra. The rotational solutions that we have can help us explain microwave spectroscopy, which rotates a molecule. So we'll use these models to understand chemical systems as we go through the rest of the class.